So the last thing in Unit 3 we're going to go over are applications of these linear equations. And what we're going to do is use them to solve what's called system of equations. So basically what's going to happen is we're going to need to kind of find where two lines collide. So something that satisfies both of them. So maybe we need a cost function to equal a revenue function. Maybe we need to figure out which company is going to be better for us to do business with. So we want to get into this idea of how to solve a system. So they're all going to be problem-solving problems. So we need to remember our specific problem-solving strategy. The first thing you always want to do is you want to understand the problem. The second thing you're going to do is you're going to come up with a plan. The third thing is you actually carry that plan out. And then the fourth thing, you're going to check if possible. Okay? So it could be mathematically, plugging it back in if that's feasible, or it could be something like just seeing if it's a reasonable answer. So now we've got equations with two variable quantities. We're going to specifically look at an example of a manager that's shipping something. So we're told a small business sent out a shipment of 3 coffee mugs and 6 promotional packets on Monday, and the total shipping weight was 42 ounces. 2 days later on Wednesday, they sent 6 more mugs and 3 more packets, and this time the weight was 48 ounces. So all we know is the total weight based on the quantity of each item we sent. What we want to know is what is the shipping weight for the packets and what is the shipping weight for the mugs. So that is our ultimate goal, knowing these two things. So we've got two variable quantities. We've got the shipping weight of a packet and the shipping weight of a mug. So we're going to let X represent the weight of one mug, and we're going to let Y represent the weight of one packet. So we want to write an expression that describes the combined weights of 3 mugs and 6 packets. So we have 3 mugs that are X ounces each, and we've got 6 packets that are Y ounces each. And so the total weight would be the addition of these two quantities. We just don't know what X and Y are. That is our goal. We want to find them. But this is the total weight of that first shipment, so this better equal 42 ounces. Okay? So now we're going to do the same thing for the second shipment. We had, in the second one, 6 mugs and 3 packets, and the total weight was 48. So for the second shipment, we had 6 mugs, which are X ounces each, and 3 packets, which are Y ounces each. And in total, that equals 48. Okay? So what we get are 2 linear equations, and both of them talk about the same type of idea. There better only be one value of X and Y that satisfies both of these. Because magically from one day to the next, my shipping weight per item isn't going to change. My mugs aren't going to cost, or going to be 10 ounces this day and 9 ounces the next day. It's always going to be exactly the same. So what we want to do is we're going to try to solve this in a few different ways. We're going to go through it with a table, we're going to go through it graphically, and then we're actually going to solve this algebraically. So first thing we're going to do is for each of these equations, we're going to solve for Y. So we've got 3x plus 6y equals 42. So to solve for y, we first have to subtract 3x from both sides. So that gives us 6y is 42 minus 3x. So to get y on its own, you divide everything by 6, and that gives us y is equal to 42 over 6, which is 7, and then 3 over 6 is 1/2. So our first equation is y equals 7x, 7 minus 1/2 x. For the second equation, we have 6x plus 3y equals 48. We're going to do the same thing. We want to solve for y, so bring the x to the other side. And that gives us 3y is 48 minus 6x. And so we divide by 3 to get y on its own. That gives us y is equal, 48 divided by 3 is 16. Negative 6 divided by 3 is 2. So now we're going to make a table of values for each equation. So we've got this first equation here. I'm going to plug in the values of x and see what y is in this chart. Okay. So if we plug in 2, we're going to get 7 minus 1/2 times 2. You're going to find out this is 6. If you plug in 4, you get 1/2 times 4, which is 2. So 7 minus 2 would be 5. If you plug in 6 for the next one, you'll end up with 4, and then plug in 8 will be 3, and then plugging in 10 will be 2. Now we're going to do the same thing with the second equation. We've got y is equal to 16 minus 2x, and I'm going to plug in the same values of x and see what y has to equal. Okay. So if you plug in 2, you get 16 minus 4, so this would be 12. Plug in 4, you get 16 minus 8, so 8. Plug in 6 is 16 minus 12, so 4. Then you would get 0. And then finally, if you plug in 10, you get negative 4. So one thing you can kind of notice, again, I need a solution that satisfies both of these. If I look right here, when x is 6, both of the y values are 4. So what that's going to tell me is for 6 ounces, the y is the same. So the x and y are the same for both equations, which is exactly what we want. Okay? Because I want a solution that works for both of them. The same x and y have to satisfy both equations. So if we go ahead and graph these two, we've got y equals 7 minus 1/2 x. And then we've got y equals negative 2x plus 16, or 16 minus 2x. If we go ahead and plot these, let's plot this first line. When x is 0, y is going to be 7. And then you can pick out some other points. When x is 2, then the y value is 6. When x was 4, the y value was 5. When x is 6, the y value is 4. And then you get your line. So here is our first line that would continue on. If you plot the second line, let's do that one in green. I can't really plug in 0 because I don't have a spot for it on the graph. But if you plug in x equals 2, the y value is 12, still can't plug that in. When you plug in x equals 4, the y value is 8. X equals 6 gives you a y value of 4. 8 gives you a y value of 0, and then it would just be down from there. So there is our second line. So this is the point here at 4, 6, where those lines look like they intersect, or 6, 4. X has to go first. So at 6, 4, the two lines intersect. So this means the x and y values are exactly the same and it satisfies both equations. Okay? So if you plug these coordinates back into the original equation, let's see what we're going to notice. We've got 3x plus 6y equals 42. And we've got 6x plus 3y equals 48. And we're going to plug x is 6 and y equals 4 into both equations. So remember, it goes x, y, always alphabetical order. So we get 3 times 6 plus 6 times 4 equals 42. That's 18 plus 24 equals 42. And that's just 42 equals 42. So you get a true equation here. If you do the same, you get 6 times 6 plus 3 times the y value is 4. That needs to equal 48. 6 times 6 is 36. 3 times 4 is 12. So indeed, we get 48 equals 48. So you get another true statement. So the solution tells us that when x equals 6 ounces and y equals 4 ounces, this makes my first shipping day equal 42 ounces, and my second shipping day also equal 48 ounces. So it's a solution to both equations. In all of these other ones, technically, if you let x equals 6, or y equals 6 and x equals 2, that works for this first equation. It is a possible weight for these. However, if you try to plug 2 and 6 into the second equation, it's not going to work. You would have to plug in 12 to be able to make that a statement. So our goal was to find a x and y value that satisfied both equations simultaneously. So this solution, the one that satisfies both, tells us this is exactly what the weight is of each object. So x was the mug. The mug weighs 6 ounces. And then that tells us the packet weighs 4 ounces. So that was the y value. Okay. So that is our solution to this equation. A solution to a system of two equations is a pair of numbers, one for each of the unknown variables, that make both equations true when substituted in. Solving a system means you're finding all pairs of numbers that are a solution to both. So you really didn't have to go through all of these processes. They're all going to work. You do get this same point. But really from this chart, seeing that we got exactly the same y value for this input tells you it's the solution. So there's a multitude of ways you can find it. But from the table, you can see when x equals 6, both equations have the same y value. So we didn't need to go through graphing in that process. Okay? So now this can be really tedious. We want to go through a more algebraic way to solve the system. So what we're going to do is kind of utilize that we solved both of these equations for y. So we had started with 3x plus 6y equals 42. And when we solved this, we got y was equal to negative 1/2 x plus 7. Okay? Our other equation was 6x plus 3y equals 48. So what we're going to do, these y values better be exactly the same. It's the same weight of the packet. So instead of this value of y, I'm going to replace it by what y is from the first equation. So we get 6x plus 3 times the y value, which is negative 1/2 x plus 7. And this needs to equal 48. So if you notice now, as a result of plugging in this value of y, we only have a single variable, which is x. So we can go through and we can now solve this resulting equation for x. So we've got 6x plus 3 times negative 1/2, so that's just negative 0.5, x plus 7. This needs to equal 48. So to solve for x, we're going to have to distribute this 3. So we get 6x, 3 times negative 1/2 is negative 1.5x. 3 times 7 is 21. And this needs to equal 48. So if we combine the like pieces, we have x and another x. So we've got 6 minus 1.5. In total, we have 4.5x plus 21 equals 48. So go ahead and subtract 21 to be able to solve for x. And that gives us 4.5x equals 27. So to solve for x, you just divide by 4.5. And you still get that x is going to equal 6. So it still ends up in the same result. And now the y value is negative 1/2 x plus 7. So the y is going to equal negative 1/2 times 6 plus 7. So that's y equals negative 3 plus 7. And we still get the same solution. So it still works out. You get x to be 6 and you get y to be 4. So same solution, but you didn't have to go through graphing or creating a table. We're able to solve it algebraically. So this is going to be that idea that we're going to follow. The first thing you should do is you should solve one equation for one variable. You can pick either one. Plug that back into the other equation, and then that's going to make it so it's a single variable equation, which you can then solve. Once you go through and you find what that value is, you're then going to go back and plug it into whatever variable you solved for from the first step. So let's go ahead and let's do some more examples, because the best way you can kind of go through this is just by lots of practice. So when traveling on business, Eldrick bought a $50 prepaid international cell phone to call his girlfriend. Calls cost 7 cents per limits. How many minutes has he used if the display is showing a balance of $32.15 remaining? So the answer we could think about in two questions, or this question we can think of with two different equations. One tells us the value of the card is $32.50. So if we want to write that as an equation, the value, V, is $32.15. Now another equation tells us our original value starts at $50 and it's going to decrease by 7 cents each minute used. So we're starting out at 50, so that's our y-intercept, and the value is that minus the 7 cents times the number of minutes. So we can complete a table if we'd like with these two equations. The first equation is just the V equals $32.15. So the value in my card is this. And the second equation is V is equal to 50 minus 0.07x. So regardless of the value of x, the first equation tells us the value is always $32.15. Okay. So So the output is always 32.15. For the second equation, if we plug in all of these values, so plug in 0, the value starts out at 50 bucks. If you used 100 minutes at 7 cents each, that's going to mean you've used 7 bucks. So when you plug it in for the value of X, you get 43. Likewise, if you plug in 200, you get 36. You'd get 29, 22, and 15. So we run into a bit of a problem here. Unlike the last example, you're not going to be able to clearly see where these two are intersecting because you'd have to go down to a nitty-gritty details. So if we try to graph it, maybe we're going to get a better idea. All I know is right now, it's going to be somewhere between 100 and 200 minutes. Because $32.15 falls somewhere between these values. I just don't know where yet. So if we do graph them, the first one is the value is always $32.15, which is right around here. So here's V equals 32.15. So the value is always this. The second equation, you start at $50, and then after 100 minutes, you're down to 43. After 200 minutes, you're down to 36. And then 300, we're a little less than $30. And then the equation of our line would look like this. So that's V equals the 50 minus the 0.07x. So from the graph, which isn't going to be perfect, it looks like they're intersecting around here. So maybe about $220 or 220 minutes and $32.15 is the solution, but it's not exact. So this turns into a problem when we use the table or estimation. You can't always plug and chug and try to just guess. What we're going to do instead is solve this algebraically. We know V is $32.15, and then the other equation we have is V equals 50 minus 0.07x. Well, this V better be the same as this one, so go ahead and substitute that in. So we're going to go ahead and substitute that in. We're going to get $32.15 is equal to 50 minus 0.07x. So to solve for x, we'll go ahead and subtract 50 from both sides. And that's going to give us negative 17.85 is equal to negative 0.07x. To get x, you divide by negative 0.07, divide by negative 0.07, and that gives us x is equal to 255 minutes. So he used 255 minutes, so you can kind of see we are way off. Our graph was not perfect because we had to estimate kind of where things were, so it's a little bit problematic. So our estimate is very off. Okay. So although estimation is good, it gives you an idea, it's not perfect. But now we want to see what the second coordinate of the solution is. So what we're going to do is just plug x equals 255 into either equation. Really, this first one's going to be the nicest because V is always equal to 3215. But I'll go ahead and plug it into the second equation so you can see it still also satisfies it. So if you plug in X is 255 into this equation, you still get 3215. So the solution is he's used 255 minutes, so the remaining balance on his card is $32.15. Okay. So now let's go ahead and work through some more problems. Again, try to do this on your own if you can, and then just kind of revert to this if you have questions. So the members of an intramural softball team decide to get custom t-shirts made. There are 2 screening shops in town which they can choose from. Wave Graphics charges a $32 or setup fee of $22, and each additional shirt is $7. Shirt Shack doesn't charge a setup fee, but they have a higher cost, which would be $3 or $9 per shirt. If for some bizarre reason the team decides to order 3 shirts, which shop would be cheaper? So let's first look at the Shirt Shack. That one's a little bit simpler. You're going to order 3 shirts. It's $9 per shirt. So it would be $27 to order 3 shirts from the Shirt Shack. For the Wave, they charge $7 per shirt. So it'd be 7 times 3. But then they charge you that $22 setup fee. So in total, you're going to spend $43 if you go to the Wave Graphics for 3 shirts. So the Shack is definitely cheaper. Okay. So what we want to do is we really kind of want to see the break even. So then I know based on how many shirts I want to order, am I going to go with the cheaper option or am I going to go with the more expensive? So it's kind of that cutoff point. The Shirt Shack will be cheaper just because they don't have that setup fee for values that are less. And then the Wave Graphics would be cheaper if you're going to order more than this break even. So if we think of the Shirt Shack, we're going to let X be the number of shirts and C is going to be the cost. So they charge $9 per shirt. The cost is just 9X. For Wave Graphics, they charge $7 per shirt, which is 7X, but then they have that $22 initial fee. So we've got a system of equations. The Shirt Shack is 9X, and the Wave Graphics is 7X plus 22. So let's go ahead and plug in some numbers of shirts and see when is that break even going to be. So first let's go through Shirt Shack. When you buy 3 shirts, we've seen it's 27. 6 would be 9 times 6, so it'd be $54. 9 would be 81. 12 would be 108, and 15 would be 135. For Wave Graphics, we saw when we ordered 3 shirts, it'd be $43. For 6 shirts, 7 times 6 would be 42, plus another 22, you'd get $64. Then you'd see it's 85, 106, and 127. So originally, for these values, the Shirt Shack is going to be cheaper. However, from this point onward, it's going to be cheaper to go with Wave Graphics. So at some point between 9 and 12, that switch happens. We don't know exactly when it is, but it's probably going to be closer to 12 because that's when those numbers are even together. So maybe we would think about 11 shirts would be a good estimate of when they would cost exactly the same. Right? So let's go ahead and graph these two equations on the same plane, and then we're going to see what their intersection looks like maybe a little bit better. So we're going to put the number of shirts on the x-axis, and we're going to put the cost on the y-axis. Let's go ahead and zoom in. So we need to go up to at least 12. So let's do 2, 4, 6, 8, 10, 12, 14, 16, 18 shirts. And let's just make the cost go up by a nice number. Let's go ahead and go up by 20s. So 20 bucks, 40, 60, 80, 100, 120, 140, 160, 180, and that'll be good. So for the shirt shack, if you order no shirts, it's no dollars. If you order 2 shirts, it's around 18. If you order 12 shirts, it's going to be $108, which is right around here. So this would be our shirt shack. If we look at the next one, you have that initial $22 setup fee. So no shirts, still 22 bucks. 12 shirts is $106, so it's a little bit less than this one. And then we can connect those dots. Okay. So this here is Wave Graphics. Okay. So now we can look at their intersection a little bit better. It looks like, yeah, it is around 11 shirts, somewhere in between 10 and 12. So now we want to answer some questions based on this graph. What does the height of every point on the line represent? And so that's basically what is the y value, and that is the cost for X shirts. Okay. The points where the graphs cross is where the two heights are the same. So what does that represent? They're both representing cost, so this would be where the costs are the same. And then based on our graph, what is that cost that makes them about the same? And so their intersection happens around when x equals 11, so probably about 11 shirts is when the cost would be equal. So now we're going to go through and we're actually going to solve this algebraically. We've got the cost is 9x, and then we also have the cost is equal to 22 plus 7x. Well, these c's better be exactly the same. So instead of c, we're going to replace it by 9x, and that better equal 22 plus 7x. So to solve for x, let's bring all the x's to one side. So let's bring the 7x over. That gives us 2x equals 22. Divide both sides by 2, and we get x equals 11. So that tells us the shops cost the same. For 11 shirts. Okay. So if we look back, if we want to order less than 11 shirts, it's going to be a good idea to go with the shirt shack. If we want to order more than 11 shirts, Wave Graphics is going to be cheaper for the cost. And at 11 exactly, it doesn't matter. That's where they're the same. So we want to see what is the number, or what is the total cost then. So let's look at the shirt shack. the cost is 9 times the number of shirts. So the cost is 9 times 11, or it'd be $99 to order the shirts from Shake or Shirt Shack. For Wave Graphics, the cost is 7x plus 22. So for 11 shirts, it would be 7 times 11 plus 22, which is also $99. So the cost is $99 for both locations. Okay. So now that we practiced this, let's work with kind of some other suggestions. So the Shirt Shack operates on a daily fixed cost plus a variable cost that depends on the number of shirts screened in one day. The total cost for screening 260 shirts was $1,015. For screening 380 shirts, their cost was $1,450. So our goal is to figure out what is this fixed daily cost and what is the cost to screen each shirt. So there are two unknowns we have. The first one is the fixed daily cost. So let's make that X. We don't know this. And then the second one is Y. That's the cost per shirt to screen. So we want to use these two variables and these two pieces of information to write a system of equations and solve it. So the first tells us 260 shirts cost us $1,015. So the first one, we have the fixed daily cost. We screened 260 shirts, and that cost Y dollars each. And in total, the cost for the day was $1,015. For the second day, 380 shirts cost us $1,345. So we have the fixed daily cost for the second day, and then 380 shirts at Y dollars each. Adding these together gives us the total amount of $1,345. So we have our two equations, which we now can solve. So the easiest variable to solve for is X. So we've got, let's go to a new page. The easiest variable to solve for is X. So we've got X plus 260Y equals 1,015. And then we've got X plus 380Y equals 1,345. If we solve this first equation for X, we just subtract negative 260Y from both sides. So X is equal to 1,015 minus 260Y. So these X's better be the same. So I'm going to replace the X by this new quantity that just deals with Y. So plugging it into the second equation, X plus 380Y equals 1,345. The X is 1,015 minus 260Y. Then plus 380Y needs to equal 1,345. Okay. So now we group our like pieces. We've got negative 260Y, positive 380Y. So we've got 1,015 plus 120Y equals 1,345. So finally, to solve for Y, subtract 1,015. And that gives us 120Y equals 330. So we're almost there. Just divide by 120 to get Y. So the Y is equal to 2.75. Okay. And now that we know y, we can solve for x. X is 1,015 minus 260 times y. So plugging in the value of y, which is 215, we get x is equal to 300. So our fixed daily cost is this 300, and the cost per shirt is $2.75.